Hello, my name is Nikky LaBranche, and today I will be talking about the characterization of particulates in Australian mines. For those of you that don't know me, I'm originally from the US. I graduated from Virginia Tech and used to work at NIOSH Pittsburgh. Here in Australia, I spent a number of years working for the Queensland Government in health and safety research, and now I'm at the Minerals Industry Safety and Health Centre, aka MISHC, within the Sustainable Minerals Institute at the University of Queensland. David Cliff and I started an ACART project on the monitoring and control of respirable dust and are currently undertaking a strategic gap analysis of particulates with industry support from Glencore Copper and Resources Safety and Health Queensland, RSHQ. I'll start with a bit of background on Australia and the mining environment before I get into the characterization data. Australia is roughly the size of the US, with most of the coal concentrated along the east coast in the states of Queensland and New South Wales. Australian mining legislation is state-based, with each state having its own legislation and systems. The states cover a large amount of land and a variety of mining types. Queensland, for example, would cover roughly the area from Maine down to the Carolinas and over to the Mississippi River. In Queensland, there are 40 open-cut coal mines and 8 underground coal mines producing 240 million tons per annum. This translates to roughly 8,000 underground coal mine workers in Queensland, working in only a handful of seams. In New South Wales, there are 41 coal mining operations. This includes 20 underground mines, 16 of which are longwall operations, and 21 open-cut coal mines. In Australia, most of the coal mines are owned by large multinational corporations. There are no small mines that employ only a handful of people in coal, like there are in quarrying and opal sectors. Australian coal seams tend to be very tall, with seam thicknesses up to 26 feet or 8 meters. 6 of the 8 mines in Queensland are longwall mines, and the other 2 are room and pillar. There are top coal caving longwalls used, and some of the high-reach longwalls mine up to 15 feet or 4.5 meters. Most of what is produced is metallurgical coal, and Queensland has 35 billion tons of high-quality coal reserves. Continuous miner development is done predominantly with miner bolters, as opposed to cut and flit with separate mining and bolting units. The industry is very safe with only a small number of fatalities annually. Both Queensland and New South Wales have compulsory health surveillance schemes, which means every coal mine worker is periodically checked, including a chest x-ray. In New South Wales, it's every 3 years for underground coal miners and 6 years for everyone else. In Queensland, it's every 5 years for all workers. Queensland has recently implemented the health surveillance scheme for metal mines and quarry workers as well. Having a compulsory health surveillance scheme means there's a much better chance of catching cases as they progress. There's also a robust universal healthcare system and workers' compensation scheme. In Australia, exposure monitoring is on the individual person and not the designated operator. This is in contrast to measuring continuously over a shift for that role that does not allow for breaks or job rotation. As such, the dust exposure would be expected to be higher for the designated operator than for an individual being monitored. Prior to the re-identification of CWP in Queensland, the exposure limit was 3.0 milligrams per cubic meter with shift adjustment. Queensland mines normally work 12-hour shifts, 7 days on and 7 days off. In Queensland, the sampling is performed by fee-for-service hygiene consultants, and different consultants use different brands of sampling equipment. Sampling is measured from portal to portal, meaning hygienists don't always go underground to observe conditions and may rely on the worker being sampled to fill out a report on their activities for the day. In New South Wales, the exposure standard of 2.5 milligrams per cubic meter was adopted in 2004 when the flow rate changed to 2.2 liters per minute. No shift adjustment is applied. Compliance sampling is performed by Coal Services, the statutory body, so all sampling is done using the same fleet of equipment and a consistent approach. Most of the coal services personnel are ex-deputies with mining experience. During sampling, coal services inspectors go underground to observe the workers and talk to them about their dust control and operator positioning. Samples are taken from crib room to crib room, the Australian term for dinner hole, which means samples are of shorter duration and don't count the travel time to and from the section. Both Queensland and New South Wales have moved to a lower exposure standard of 1.5 milligrams per cubic meter. Coal Services uses the Casella-Higgins dual type cyclone-elutriators. Queensland uses both the Casellas and SKC. The SKCs were found to be oversampling by 30%, so the flow rate was changed from 2.2 liters per minute to 3.0 to compensate for this difference. This figure illustrates the mine dust lung diseases reported to Resources Safety and Health Queensland as of 31 August 2020. The teal color represents the cases of coal workers' pneumoconiosis, while the black represents cases of silicosis. As you can see, the majority of cases are not CWP. In fact, only about a third are CWP, and a growing number are silicosis and COPD. From 1984 to present, there have been 177 cases of mine dust lung diseases reported in Queensland. 73 of these are non-pneumoconiosis cases. 45 cases of CWP have been reported, along with 40 cases of silicosis and 19 cases of mixed dust pneumoconiosis. New South Wales reported 5 cases of CWP at the end of 2019. There have also been a number of cases of silicosis reported by engineered stone benchtop workers. These can be very aggressive and affect younger workers after only a few years due to the high silica content in engineered stone. As of the end of 2019, there were 350 cases reported, most of them in Queensland. Controls have been put in place in some states to ban uncontrolled dry cutting and grinding of engineered stone benchtops. This graph shows a comparison of the chemical composition of the respirable dust in continuous minor sections in the US versus Australia. The US data came from Emily Sarver's 2019 paper. I took the Australian samples and sent them to Virginia Tech for analysis. The light blue is the carbonaceous material, which includes the carbon particles, which is both the coal dust and the diesel particulates. The automated routine used here can't distinguish between the two, but I'll talk more about the diesel later. There is a large portion of aluminous silicates in orange and some silica represented in red. The carbonates are mostly stone dust, and there are occasionally heavy metals or other particulates present. Except for mine 3, who was cutting a section with stone in the working section, the Australian mines seem to have relatively more carbon in the samples than the US. This may be because Australian mines are typically leaving coal roof and coal floor. I'm currently working on further sampling of the underground coal mines in Australia, which are being analyzed in-house by the Minerals Liberation Analyzer, or MLA. These samples are from 3 mines that are different mines and seams than the previous slide, so a direct comparison of methodologies cannot yet be made. The major trends hold the same, with relatively more carbon in the samples and just a small amount of quartz. This method reports on 26 minerals, but I've removed the minor components for clarity, so you may notice some don't add up to 100% now. Not all mine dust has a uniform particle size distribution. It can vary quite considerably from one mine to the next. This figure shows the count of particles in 3 size classifications for continuous minor sections in 4 different underground coal mines in Australia. As you can see, the particle size distribution varies from mine to mine, even for the same type of mining process. The particles less than 2 microns in size account for between 55 and 80% of the size distribution, while the particles over 4 microns only account for less than 14% of the samples. But when the particles larger than 10 microns appear on the filter, they do contribute a much more significant portion of the mass. For instance, for MIND 3, particles over 10 microns account for only 0.5% of the count of particles, but 18% of the mass on the filter. Minds with a greater number of large particles may have a harder time complying with statutory limits, but may not necessarily pose more of a health hazard. Cyclone elutriators measure aerodynamic equivalent diameter and not strictly particle diameter. Even so, some of the large particles that are being found on the filter are significantly over 10 microns. On the right is an example of a large particle measuring 33 microns found on one of the filters sampled with the SKC cyclones at the original 2.2 liters per minute. The table on the left is from the further sampling in the Australian mines. These were conducted with Casella cyclones. If you look at the P50 line, this is showing the particle diameter at which 50% of the mass passes. Even within samples from 2 mines, this can vary from a low of 1.9 microns on filter 2004 to a high of 7.3 microns on filter 2009. This figure shows the particle size distribution for the carbon, aluminosilicates, and silica for mines 2 and 3. These were calculated by measuring the largest dimension of each particle and assigning them to the appropriate bin, which is 0.1 microns in size. In mine 2, there were 1,250 particles counted, and in mine 3, there were 1,542 particles counted. As you can see, the chemical compositions are very different. For mine 2, on the right, the carbon particles dominate, and a number of aluminosilicate particles are present. There is, however, very little silica present in this sample. Mine 3 is very different in nature. For mine 3, the aluminosilicates dominate the sample, and there is also a large number of silica particles present, especially in the smaller size fraction. There is almost no coal in the sample, as illustrated by the blue line on the bottom. As I mentioned, the automated routine in this methodology looking at the carbon particles cannot distinguish between coal and DPM. However, the DPM particles have a unique shape and they can be picked out on the SEM field manually. In this photo, you can see the chains of agglomerated diesel particles all over the filter. The black dots you see are the pore spaces in the filter, which are 0.4 microns. When diesel particulates are generated, they are normally in the nanometer range. Agglomeration involves the growth of particle chains and clusters through collision of the particles. We don't know if this agglomeration took place on the filter or if it was picked up like this through agglomeration in the mine. If it was picked up in the mine, this would suggest that if you're trying to measure diesel particulate matter, that direct measurement of PM1 would be an underestimate of concentration. This is more diesel than I expected to find and is a subject of further investigation in my studies. That concludes my presentation, and I want to thank you very much for listening. I hope this gave you an idea about how the challenges we face in Australia compare to the US and how different the characterization can be. It also illustrates how different silica content and size distribution can be in different seams. MSHA is currently working on a gap analysis of particulates in the mineral sector, which aims to identify the current gaps in our understanding of particulates and identify areas for future research. I'm still in the process of putting together the findings from the analysis conducted so far in the coal mines. There are plans to start sampling in the metal mines as well. I'm hoping to use what we learn about the characterization of dust, including the particle size, shape, and chemical components, to help the mines better control their dust at the source. A further research goal of mine is to try and relate the characterization to the potential health impacts, which I feel I have a unique opportunity to do given a small number of mines and a compulsory health scheme to detect cases of mine dust lung disease. Please feel free to get in touch with me if you have any further questions. Thank you.